Silence. Not the kind you hear on Earth. A deeper silence. A silence so complete it feels heavy. You are standing on the moon, but not the moon you've seen in photos, not the bright, glowing surface lit by sunlight. Here, the sun never rises. There is no horizon glowing orange, no shadows slowly moving with time, only darkness, endless, frozen, permanent. The ground beneath you is locked in ice colder than anything on Earth, colder than Antarctica, colder than the deepest freezers ever built by humans. Minus 230 degrees Celsius. Metal becomes brittle, electronics slow, then die. Batteries drain in moments. Even the idea of warmth feels impossible. You cannot feel the wind, you cannot hear sound, and above you, the sky is not blue. It is pitch black, scattered with unmoving stars. This place has not seen sunlight for billions of years. Now imagine standing here completely alone. No shelter, no rescue, no second chances. Every step could send you sliding into a crater so deep that radio signals struggle to escape. Every shadow could hide sharp rocks capable of tearing through machines designed to survive space. This is not science fiction. This is not a nightmare. This is real. Spacecraft have failed here. Millions of dollars have vanished into the darkness. Years of work erased in seconds. And yet, scientists keep coming back. They aim their most advanced technology at this frozen abyss. They risk missions, reputations, and lives. Not because it's easy, not because it's safe, but because something is hiding here. Something so valuable. It could change the future of humanity forever. So the question is simple. Why would scientists risk everything to go to the darkest, coldest, most dangerous place on the moon? What is the most dangerous place on the moon? When scientists talk about the most dangerous place on the moon, they are not talking about explosions, lava, or collapsing ground. They are talking about the moon's south pole, a region that looks calm and silent from orbit, yet becomes one of the most hostile environments ever studied once you get close. This area sits at the very bottom of the moon, where sunlight barely grazes the surface and, in some places, never arrives at all. Hidden within this region are craters unlike anything on Earth. Craters are so deep and so perfectly positioned that their interiors have remained in darkness for billions of years. Among them, 3 names appear again and again in scientific research: Shackleton Crater, Cabeus Crater, and Hayworth Crater. These are not just impact scars, they are natural traps of darkness and cold, preserving ancient material untouched since the early solar system. Shackleton Crater lies almost exactly at the moon's south pole. Its rim is one of the few places on the moon that receives near-constant sunlight, while its interior never sees the sun at all. Just a short distance away, Cabeus Crater gained global attention when NASA deliberately crashed a spacecraft into it and detected water ice in the debris. Hayworth Crater goes even deeper, with temperatures that rival the coldest places known in the entire solar system. This place is not dangerous like a volcano or an earthquake zone on Earth. Nothing explodes, nothing moves quickly. The danger here is slower and far more unforgiving. On Earth, humans can survive extreme cold with air, shelter, and fire. At the moon's south pole, there is no air, no heat, and no natural protection. One system failure does not mean discomfort, it means total mission loss. On Earth, night eventually ends. Temperatures rise. Rescue is possible. At the moon's south pole, night can last forever. A single shadow can be colder than deep space. A single miscalculation can send a spacecraft into darkness it can never escape. This is why scientists do not call it dangerous out of fear. They call it dangerous because survival here is nearly impossible, and yet the rewards hidden in this darkness may be worth everything. A place without sun. There are places on the moon where night does not last for hours or days, but forever. Near the South Pole, the sun hangs so low on the horizon that some craters are never reached by its light. These are called permanently shadowed craters, and they exist because the moon's axis is barely tilted. As a result, sunlight skims the surface and completely misses the deep interiors of certain craters, leaving them in eternal darkness. Inside these craters, temperatures plunge to extremes that feel almost unreal. Scientists have measured surface temperatures below minus 230 degrees Celsius, making them colder than Pluto in some cases. These are among the coldest naturally occurring places in the entire solar system. The cold is not temporary or seasonal, it is constant, relentless, and and unchanged for billions of years, locked in place since the moon's early history. Some of these shadowed regions have not seen sunlight for over 3 billion years. Long before dinosaurs walked the Earth, before complex life even existed, these craters were already dark. Time behaves differently here. There is no erosion by wind, no rain, no warmth. Everything that enters is preserved, frozen in a near-perfect snapshot of the ancient solar system, turning the moon's south pole into a vault of cosmic history. In such a cold, even machines struggle to survive. Metal becomes brittle, losing its strength and cracking under stress. Lubricants freeze solid. Electronics slow down until electrical currents can no longer flow. Batteries, which rely on chemical reactions, rapidly lose their ability to function. A rover or lander entering permanent shadow risks shutting down completely, not because it is damaged, but because physics itself works against it. For a human body, the danger is immediate and absolute. Without sunlight or atmosphere, heat escapes instantly. Body temperature would drop rapidly, blood circulation would fail, and exposed tissue would freeze within moments. There is no warning and no gradual adjustment. Survival here depends entirely on technology, and even the smallest failure would be fatal. In permanent shadow, darkness is not just the absence of light, it is an active threat. And yet, this darkness is not empty. It is not meaningless. The same cold that makes survival nearly impossible has preserved something ancient and fragile, something that should not exist here at all. Locked inside this frozen silence, protected from sunlight for billions of years, lies a discovery that changed everything. But something impossible survived here. Terrain that destroys spacecraft. Imagine descending toward the moon, engines firing, fuel ticking down second by second. From orbit, the surface looked smooth and silent, but as the spacecraft drops lower, the illusion disappears. The moon's south pole is carved with steep crater walls that plunge sharply into darkness. Some slopes are so steep they rival cliffs on Earth, offering no safe, flat ground for a landing. One wrong angle, one unstable surface, and the spacecraft has no way to recover. As the lander approaches the ground, the terrain becomes even more dangerous. The surface is littered with jagged rocks formed by billions of years of impacts, untouched by erosion. Many of these rocks are sharp enough to damage landing legs or puncture sensitive components. Unlike Earth, there is no atmosphere to soften impacts or smooth the landscape. Every rock remains exactly where it fell, turning the landing zone into a frozen minefield. Navigation near the South Pole is a nightmare. The sun sits extremely low on the horizon, casting shadows that stretch for kilometers. These shadows distort depth perception, making small bumps look like cliffs and shallow craters appear bottomless. Cameras and sensors struggle to interpret what they see, feeding confusing data into onboard computers that must make split-second decisions without human control. For modern spacecraft, artificial intelligence plays a critical role during landing. The system must analyze terrain, identify hazards, and choose a safe landing spot in real time. But at the moon's south pole, long shadows and extreme contrasts can confuse these systems. A shadow can look like a deep pit, a flat surface can vanish into darkness. The lander is effectively navigating half-blind, trusting algorithms to interpret a landscape humans have never walked. This is why missions have failed here. Some spacecraft lost control during descent. Others misjudged terrain and impacted the surface at high speed. Years of engineering, planning, and testing ended in seconds. These failures were not due to poor design, but because the environment itself pushes technology to its limits. The moon's south pole offers no forgiveness for even the smallest error. In many ways, landing here is even harder than landing on Mars. Mars has an atmosphere that helps slow spacecraft during descent. The moon has none. Mars receives regular sunlight and offers clearer terrain mapping. The moon's south pole hides its surface in darkness and shadow. Every landing attempt becomes a gamble against gravity, fuel, and uncertainty. As fuel runs low and the ground rushes closer, the countdown reaches its final seconds. There is no turning back. The engines fire, the shadows rise, and the spacecraft must decide, alone, whether it will touch down safely or become another silent wreck in the dark. Communication and navigation nightmare. For spacecraft operating here, this creates a serious problem. Communication antennas must maintain a precise line of sight to Earth, and even a small obstruction can weaken or completely block the signal. In a place filled with deep craters and towering rims, staying connected becomes a constant struggle. When signals weaken, data does not flow smoothly. Commands sent from Earth can arrive late or not at all. Telemetry becomes incomplete, distorted, or silent. Engineers may see a lander descending, but they cannot guide it in real time. At this distance, even light-speed communication creates a delay, forcing mission teams to trust that pre-programmed instructions will work exactly as intended. Because of these delays and dropouts, landers must make autonomous decisions during the most dangerous moments of a mission. Computers on board analyze sensor data, adjust thrust, and avoid hazards without human input. There is no joystick, no emergency override. If the software misinterprets the terrain or receives corrupted data, the lander will not ask for help. It will act on its last instruction, even if that decision leads directly toward disaster. As a spacecraft descends, the margin for error shrinks to almost nothing. A miscalculation of altitude by a few meters can result in engines shutting down too early. A slight delay in thrust can cause a hard impact. In the final seconds, there is no time to correct mistakes. The system must be perfect because gravity will not wait. Then comes the moment every mission team fears. The signal begins to fade. Telemetry numbers stop updating. A few seconds pass, then silence. Engineers wait, hoping the connection will return, hoping the lander has survived behind a ridge or within a shadow. Static fills the channel. No confirmation, no signal, just a quiet realization that something has gone wrong. In space exploration, failure does not announce itself with explosions or alarms. It arrives quietly as a missing signal and an empty data stream. At the Moon's south pole, that silence often means a spacecraft has become another unseen casualty, resting forever in the dark. Missions that failed. The Moon's south pole is not just dangerous in theory, it has already claimed missions. Over the past decade, multiple spacecraft aimed for this region and never made it back. These were not experimental toys, they were the result of years of planning, international collaboration, and budgets reaching into the hundreds of millions of dollars. Each failure left behind debris scattered across a surface no human has ever visited. The spacecraft was performing normally until the final descent, when communication was suddenly lost, just kilometers above the surface. Engineers watched live telemetry as data streams froze and the signal vanished. Later, analysis showed the lander had crashed near the Moon's south polar region, ending a mission that had come painfully close to success. Pole and conduct long-term scientific research. During orbital adjustment maneuvers, the spacecraft entered an uncontrolled trajectory and impacted the lunar surface. This marked Russia's first lunar mission in decades, and its failure underscored just how unforgiving the South Pole environment remains, even with modern technology. Private missions have not been spared either. In 2019, Israel's Bereshit spacecraft crashed during its landing attempt after an engine failure. In 2023, while not all of these missions targeted the exact South Pole, their failures revealed a common truth. Landing on the Moon, especially in difficult terrain, is still one of the hardest tasks in space exploration. For the engineers and scientists involved, these failures were deeply personal. Teams watched from control rooms as years of work ended in silence. There were no explosions on screen, no dramatic visuals, just numbers freezing, signals dropping, and the quiet understanding that the mission was over. Careers, funding, and national pride were all tied to those final moments. And yet, agencies did not walk away. They analyzed the data, rewrote software, redesigned landing systems, and tried again. Each failure revealed something new about the terrain, the shadows, and the physics of landing in permanent darkness. The cost was enormous, but the knowledge gained was priceless. So why didn't they stop? The precision of Chandrayaan-3's landing was a triumph of engineering. The mission demonstrated that landers could autonomously navigate the most challenging terrain on the Moon, adjusting in real time to avoid hazards and secure a stable position. This success was a milestone for India's space program, proving that complex lunar missions are feasible and reliable, even in areas previously deemed impossible to reach. Beyond the technical achievement, Chandrayaan-3 also validated decades of research into permanently shadowed regions. By safely landing and operating in these areas, the mission confirmed that future spacecraft could reach these craters to study water ice and other resources. It showed that the Moon's south pole is not just theoretically valuable, but practically accessible, paving the way for long-term exploration and even the establishment of lunar bases. Chandrayaan-3's success was more than a technological victory. It was a statement. The Moon's most dangerous and mysterious region could now be studied up close. What was once considered unreachable darkness became a real place of exploration, discovery, and possibility, proving that humanity can succeed even in the most hostile environments. NASA's Artemis Plan. NASA's Artemis program is humanity's bold plan to return to the moon, this time not just for brief visits, but to establish a sustained presence. The program aims to land the first woman and the next man on the lunar surface, with long-term goals of building infrastructure that could support future explorers for weeks, months, and eventually years. Artemis represents a shift from exploration for curiosity to exploration for habitation, science, and preparation for missions to Mars. The South Pole was chosen as the primary target for Artemis missions because of its unique combination of sunlight and resources. Some crater rims receive near-constant sunlight, ideal for solar power, while permanently shadowed regions contain water ice that could be mined for drinking water, oxygen, and fuel. This dual advantage makes the South Pole the most practical location for a long-term human base and positions it as the gateway to deeper space exploration. Astronauts landing here will face extreme challenges. Temperatures in shadowed craters can drop to nearly -230 degrees Celsius, and the terrain is jagged, steep, and unforgiving. Communication will be difficult in deep craters where Earth is barely visible. Every movement must be carefully planned. One misstep could end a mission. They will rely on advanced suits, autonomous rovers, and real-time monitoring from mission control. Yet the Moon's South Pole remains a place where human life has never existed. Despite the technology, preparation, and planning, Artemis will place humans in one of the most extreme environments ever attempted. It is a place of cold, darkness, and silence. And yet, it is here, in these frozen shadows and sunlit rims, that humanity will attempt something unprecedented. But humans have never stayed here. No aliens, no myths. Despite the dramatic headlines and videos claiming secret bases or alien structures at the Moon's South Pole, the reality is far more grounded in science. No evidence exists of artificial formations, no signals from extraterrestrial civilizations, and no signs of technology beyond what humans have placed there. The craters and ridges are entirely natural, shaped by billions of years of impacts and geological processes. So why do so many sources talk about mysteries or dangerous secrets? The answer lies in human fascination. Headlines use suspense and drama to capture attention, but the true intrigue is scientific. These craters are mysterious not because of aliens, but because of time itself. Some areas have been in darkness for billions of years, preserving ice, rocks, and other materials exactly as they were when they formed. This makes them invaluable for understanding the Moon's history and the early solar system. The real mystery is survival. Water ice has persisted in these shadowed craters despite harsh radiation, extreme cold, and billions of years of exposure to space. Human spacecraft and explorers face real danger in this environment, and understanding how materials, technology, and possibly life support systems can survive here is what drives research. The South Pole's allure is not science fiction. It is the ultimate natural laboratory, offering insight into time, preservation, and the boundaries of human exploration. The Moon's South Pole is a place of extremes. Darkness stretches farther than the eye can see. Temperatures drop to levels colder than any natural environment on Earth, and the terrain challenges even the most advanced technology. It is a place that has tested spacecraft, confounded engineers, and captured the imagination of scientists for decades. And yet, standing in its frozen shadows, the danger begins to transform into opportunity. Where shadows fall, water ice endures. Where sunlight never reaches, history is preserved. Every jagged crater, every hidden valley, is a potential treasure trove of resources and knowledge. The very conditions that make this region deadly are the same that make it invaluable. For the first time, humanity sees the possibility of living off this world, of turning a forbidding landscape into a stepping stone for future exploration. The South Pole is the coldest, the darkest, and perhaps the most scientifically valuable place humans have ever attempted to explore. Its frozen craters hold water that could sustain life, provide fuel, and open the door to journeys far beyond the Moon. Spacecraft and astronauts may falter, missions may fail, and yet each challenge teaches us something new, preparing us for the day we will stay longer, venture further, and explore deeper. This is not a place of myths or alien secrets. It is a place of physics, geology, and survival, a harsh teacher that demands respect and ingenuity. And within its eternal shadows lies the potential to change the future of space exploration forever. The Moon's South Pole reminds us that the greatest risks often hold the greatest rewards, It is both a warning and an invitation, a place where danger and opportunity coexist in equal measure. The most dangerous place may decide humanity's future.